First, the bad news. SAP Business AI won't help you generate cubist versions of your family's holiday photos. But it will help you understand which supplier is best to help you roll out your plant-based packaging in Southeast Asia, or identify the training your junior project manager needs to rise up the ranks, and automate repetitive tasks while you focus on big innovations, so you can be ready for the next opportunity. Revolutionary technology, real-world results. That's SAP Business AI.
Tonight in Arkansas, there's a mother tucking in her daughter and turning off the light. A business owner is burning the midnight oil. An at-home dinner date is plating up possibility. And it's all happening under one roof. How? The power of a conversation, like the one John from Integrity Solutions had with First Horizon Bank about his vision for a sustainable mixed-use building. Now it's not just words, it's life. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John. First Horizon Bank, member FDIC.
This is SpaceTime Series 26, Episode 136, for broadcast on the 13th of November 2023. Coming up on SpaceTime, a record-breaking supermassive black hole, NASA's Curiosity rover clocks up 4,000 days on the red planet, and a new view of all objects in the universe. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered the most distant black hole ever seen. The observations reported in the journal Nature Astronomy suggest that black holes were already in existence just 470 million years after the Big Bang. This black hole was discovered by combining data from NASA's Earth-orbiting Chandra X-ray telescope with the Webb Infrared Space Telescope. The black hole was discovered in a galaxy named U8C1 in the direction of the galaxy cluster Able 2744, which itself is located some 3.5 billion light-years away. However, the Webb data shows that galaxy U8C1 is much more distant than Able 2744. In fact, it's some 13.2 billion light-years away. That's a time when the universe itself was only 3% of its current age. The observations suggest that this black hole is in an early stage of growth that's simply never been seen before. It's at a point in its development where its mass is similar to that of its host galaxy. The results may finally provide an answer as to how some of the first supermassive black holes in the universe were formed. The study's lead author, Akos Bogdan from the Center for Astrophysics at the Harvard-Smithsonian, says Webb was needed to find this remarkably distant galaxy and Chandra was needed to find the supermassive black hole inside it. The authors were able to take advantage of a gravitational lensing effect, which used the mass of the foreground galaxy cluster to magnify the light from the background galaxy. Then, over 2 weeks of observations by Chandra showed the presence of the intense superheated X-ray emitting gas in the ancient galaxy, a trademark signature of a feeding supermassive black hole. The light from this early galaxy and the X-rays from the gas surrounding the supermassive black hole were being magnified by a factor of about 4 by the gravitational lens provided by Able 2744, enhancing the infrared signal detected by Webb and allowing Chandra to detect the faint X-ray source. This discovery is important for understanding how some supermassive black holes can reach colossal masses so soon after the Big Bang. See, the question's always been, do they form directly out of the collapse of massive clouds of gas, thereby creating black holes which are already tens of thousands to hundreds of thousands of solar masses in size? Or do they come from the supernova explosive deaths of the first stars, creating stellar mass black holes of around 10 to 100 solar masses, which then grow through a combination of mergers and consuming other materials such as stars, gas and planets? The trouble is, with the second method of stellar mass black holes growing, there simply isn't enough time for supermassive black holes to get as big as they do as quickly as they are. And so Bogdan and colleagues have now found strong evidence that the newly discovered ancient black hole was already born massive. Its mass is estimated to be somewhere between 10 million and 100 million solar masses. That's based on the brightness and energy of its X-ray emissions. By comparison, Sagittarius A star, supermassive black hole at the centre of our own galaxy, the Milky Way, is only about 4.3 million solar masses, and it's had at least 12 billion years to reach that mass. Another interesting fact about the supermassive black hole in U8C1 is that it has a similar mass range to that of all the stars in the galaxy in which it resides. And that's also in stark contrast to black holes at the centres of galaxies in the nearby universe, which, as our own Sagittarius A star shows, usually only exhibit about 0.1% of the total mass of their host galaxy stars. The large mass of the black hole at such a young age, plus the amount of X-rays it produces and the brightness of the galaxy detected by Webb, all agree with theoretical predictions for supermassive black holes forming not from the growth of stellar mass black holes, but directly from the collapse of huge clouds of galactic gas. This is SpaceTime. Still to come, NASA's Curiosity rover clocks up 4,000 days on the surface of the red planet, and a new view of all the objects in our universe. All that and more still to come on SpaceTime. NASA's Mars Curiosity rover has just celebrated its 4,000th day on the red planet. The car-sized six-wheeled mobile laboratory landed in Gale Crater over 11 years ago on August 5, 2012, on a mission to determine if ancient Mars could have been habitable and supported microbial life. It quickly found the answer is yes, with overwhelming evidence of past pools that would have contained liquid water and signs of what would once have been streams flowing across the planet's red Martian soil. Today, Mars is a desolate, freeze-dried world. A desert where life would find it difficult to exist. But the evidence gathered by Curiosity and its more modern twin Perseverance helps confirm that billions of years ago, the red planet was a warm, wet world, one capable of providing the sorts of conditions that would have been suitable for life to exist. Mission managers are now making sure that Curiosity, which is now in its fourth extended mission, is staying strong despite all the wear and tear from its journey so far. 4,000 Martian days after setting its wheels on Gale Crater, Curiosity remains busy conducting science. The rover recently drilled its 39th core sample, then dropped the pulverized rock into its laboratory for a detailed analysis. To study whether ancient Mars had the right conditions to support microbial life, the rover's been gradually ascending the base of the 5-kilometre-high Mount Sharp, the impact crater's central peak. I guess you can think of Mount Sharp as being a sort of geological layer cake of Martian history. The different layers were all formed at different times, and so they're providing insights into different periods on Mars, and they're recording how the red planet's climate has changed over time. This latest sample was collected from a target nicknamed Sequoia. All the mission's current science targets are named after locations in California's Sierra Nevada. Scientists hope the sample will reveal more about how the climate and habitability of Mars has evolved as the region became enriched in sulfates, minerals that were likely formed in salty water that was beginning to evaporate as Mars began drying up billions of years ago. Eventually, all the Martian liquid surface water disappeared for good. The types of sulfate and carbonate minerals that Curiosity's instruments have been identifying over the past year has helped scientists better understand what Mars was like long ago. Curiosity's lead project scientist, Ashwin Vasavada from NASA's Jet Propulsion Laboratory in Pasadena, California, says scientists have been anticipating these results for decades, and now Sequoia will tell them even more. A report in the Journal of Geophysical Research Planets shows how scientists have used data from Curiosity's chemistry and mineralogy instrument to discover a magnesium sulfate mineral called starkite, which is associated with especially dry environments like Mars's modern climate. The authors believe that after the sulfate minerals first formed in salty water billions of years ago, as that water evaporated, these minerals transformed into stachytes as the climate continued drying out to its present state. So in this way, findings like this refine science's understanding of how the Mars of today came into being. Despite having driven some 32 kilometres through punishingly cold environments, bathed in dust and radiation, Curiosity remains in good shape. But there are problems. Engineers are currently working to try and resolve an issue with one of the rover's main Mastcam cameras, the 34mm focal length left camera. In addition to providing colour images of the rover's surroundings, each of the Mastcam's two cameras helps scientists determine the composition of rocks by the wavelengths of light or spectra that they reflect in different colours. To do that, Mastcam relies on filters arranged on a wheel that rotates under each camera's lens. However, since mid-September, the left camera's filter wheel's been stuck between filter positions. The plan right now is to try and gradually nudge the filter wheel back towards its standard setting. But if that fails, scientists will need to rely on the higher resolution 100mm focal length of the right Mastcam camera, using it as the primary colour imaging system. And that will affect how scientists scout for science targets and rover routes. The right camera needs to take 9 times more images than the left to cover the same area. Scientists would also have a degraded ability to observe detailed colour spectra from rocks at a distance. Now, this isn't the first problem to befall Curiosity. Engineers have already resolved issues surrounding the wear and tear on the rover's drill system and with its robotic arm joints. And many software updates have been sent to Curiosity to fix bugs and help add new capabilities to the rover. That's made long drives easier for the rover, reducing the wheel wear and tear that comes from steering. An earlier edition of a traction control algorithm also helps reduce wheel wear and tear when driving over sharp rocks. Meanwhile, the team right now are preparing for a break of several weeks as Mars's orbit takes the red planet behind the Sun from Earth's point of view and therefore out of direct communications with the Earth, an orbital period known as solar conjunction. During this time, plasma from the Sun can interact with radio waves, potentially interfering with commands. So, engineers leave Curiosity with a to-do list for the month, and they'll wait to see what happens when they try to resume communications on November the 29th. Needless to say, we'll keep you informed. This is SpaceTime. Still to come, a new view of all objects in the universe. And later in the science report, the United States Air Force forced to blow up a Minuteman intercontinental ballistic missile during mid-flight following a technical issue. The American failure happened at the same time as the Russians also tested one of their ICBMs. That flight was successful. All that and more coming up on SpaceTime.
An avid cyclist dreams of turning his passion into a business. He consults his banker to help find the best path. Now bike wheels are being built, and all it took was a little push to get rolling. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Clint.
A team of scientists ordering the chronological history of cosmology have developed the most comprehensive chart ever created of all the objects in the universe. The research, reported in the American Journal of Physics, also offers some new ideas about how the universe may have begun 13.8 billion years ago. The study's lead author, Honorary Associate Professor Charlie Lineweaver from the Australian National University, says he set out wanting to understand where all the objects in the universe came from. Lineweaver says the universe began in a hot Big Bang. There were no objects like protons, atoms, people, planets, stars, dogs, cats, or galaxies. But of course now the universe is full of them. The relatively simple answer to where they all came from is that as the universe slowly cooled, all these objects condensed out of a hot background. To show this process in the simplest possible way, Lineweaver and colleagues made 2 plots. The first shows temperature and density of the universe as it expanded and cooled, and the second plots the mass and size of all objects in the universe. But the projects raise some important questions. It turns out parts of this plot are, well, forbidden for want of a better term. That's because objects cannot be denser than black holes. Or they're so small that quantum mechanics blurs the very nature of what it really means to be a singular object. And all that poses problems for existing cosmology hypotheses, suggesting the universe began as a singularity, which is a point of infinite density and temperature in zero volume. Lineweaver says the boundaries of the plots and what lies beyond them are also a major mystery. At the smaller end, the place where quantum mechanics and general relativity meet, is the smallest possible object, an instanton. This plot suggested the universe may well have started as an instanton, which has a specific size and mass, rather than a singularity, which, as we mentioned earlier, is a place of infinite density in zero volume. On the larger end, the plot suggests that if there really was nothing out there, a complete vacuum beyond the observable universe, the universe would be a large low-density black hole. Lineweaver admits that would be a little scary, and he says he has good reason to believe that's not the case.
I would say it's both complicated, but it's also very simple. The simple idea is that the universe started out hot and dense, and ever since it's been cooling down and expanding, and that meant that things condensed out of this hot, dense beginning.
It's the early evolution of the universe in the moments after the Big Bang and what's happened since then. How would you describe that?
I describe it as one phrase. A proton is an ice cube, is the way I like to say that. And you might think of proton as being some fundamental particle, but it's not. If in the Big Bang model, the universe started out, I wouldn't say infinitely hot and dense, but very, very hot and very, very dense. And the whole easiest way to understand what's happened to the universe is it has cooled down and gotten less dense. And when that happened, lots of objects condensed out of the background. And a proton, in that sense, is a condensed piece of water. It's a three quarks that before you had protons and neutrons, you had a quark gluon plasma. That means just very hot and very dense. And then it cooled down, and then they came together, and they bound together into a proton. So a proton is like a frozen. If water is quark gluon plasma, then a proton is an ice cube. So that's why I say a proton is an ice cube. In other words, everything you see around us, let's go backwards in time. Let's heat up everything. What happens when you heat up everything? Well, the things start to burn. So that's when molecules dissociate into atoms. You heat those up, and what happens? And the electrons go away. They get ionized, and then you have nuclei and electrons. So you have a plasma. You heat that up further, and then you get this quark gluon plasma. You heat that up further, and we're not quite sure. But the model is that it gets hotter and hotter and hotter. And what we've done is to create two plots to show the entire temperature history of the universe and the entire density history of the universe. And then we made a second plot, which we call the plot of all objects. And that means everywhere from a neutrino, electrons, protons, viruses, bacteria, houses, planets, stars, galaxies, supergalaxies, and even the entire universe. So every object you can think of, we have put on this plot. In order to do that, you have to make what's called a log-log plot. And that is not a linear plot, but a log-log plot. That gives you a larger dynamic range to include all of these objects.
It all comes to one point in space-time, I guess you'd call it, if that existed at the point of singularity, and you don't call it singularity even.
Oh, no, it's not a singularity is a word that you would only use if you thought that quantum mechanics was wrong and general relativity was the only right thing. And we know, no sane physicist will say that the only thing you need to worry about is general relativity when you're talking about the origin of the universe. That's just wrong. You need quantum cosmology. And that means you need to combine quantum mechanics and general relativity. We haven't been able to do that yet. And so some of this paper is very speculative, particularly in the first billionth of a second. But that didn't deter us from extrapolating reasonable physics that we know further back in time using very explicit but speculative assumptions about what that was like. People think black holes are very, very dense. That's completely wrong. The density of a black hole depends on its mass. The more massive a black hole is, the less dense it is. So the entire universe, by the size given by the Hubble radius, is the density of a black hole, which is kind of weird. And so the whole universe, when you plot it on this all objects plot, it falls on the line with all the other black holes.
So the Schwarzschild radius isn't just a distance between the singularity and the event horizon.
It's the size of a black hole, and you could call it the distance between the singularity, but I would not use the term singularity because we think that there is no singularity inside of a black hole. It's something else that we haven't been able to figure out. It's maybe a little bit like a singularity, but it might be a singularity that's held up, prevented from being a singularity by quantum uncertainty. So we're not sure about it.
Maybe it's a brain, a membrane for another universe? Or
I do not know, and nobody else does, and so that's beyond the scope of this paper. That's right. But the interesting thing about when you plot all these objects, you have a line where all the black holes line up on this one line called the Schwarzschild radius. And the universe lines up on that. The black hole in the center of our galaxy lines up on that. 3 million or 4 million solar mass black hole. 10 or 50 solar mass black holes also line up. These are the kind that are being discovered with gravitational waves. And even smaller black holes line up. And you can get an arbitrarily small black hole. And if you keep extrapolating, you get to a point called an instanton. This is the smallest black hole you can have. And essentially, it's called an instanton because if you have one of those, it goes, boom, immediately explodes at the Planck temperature. So it's very, very unstable. But we know that a billion years ago, 10 billion years ago, 13 billion years ago, the whole universe was on that line. It just follows that line exactly in the direction of an instanton. Whether the universe was an instanton at the earliest moments, we don't know. But it's one of the best candidates for what you might call, and others might call, the initial singularity. I would call it the initial condition of the universe. In any case, that's way above the level of this paper. The paper says, here's a plot of all objects. Isn't that interesting? Look at these other questions that it raises. And that other question is the universe a black hole? It also raises the question of how come there are no objects that are smaller than protons? Can't you get objects that are smaller than, let's say, the tau particle, which is the smallest one on here? And why aren't there particles? Why aren't there objects in this region? Why aren't there objects in that region? So it's a very informative plot, and I think it raises more questions than it answers, but I think that's some of the best science is like that.
I take it QG is quantum gravity?
Yeah, quantum gravity. You know what, we should have described that point as doubly excluded or doubly forbidden. I should have put a DF there because it's forbidden by both gravity and by quantum uncertainty.
Do you like your gravity loopy or stringy?
I don't have a preference. I'm not good enough. I'm not a good enough theorist to have any preference there, particularly because there's no good evidence one way or the other. The general relativists who are working on that are very, very theoretical, and they don't know how to do data analysis. And I know how to do data analysis, but in order to do that, you need data, and they don't have any data. So I am uninformed and have very few theoretical prejudices either way on that.
Out of the many mysteries which come out of this, what's the one that intrigues you the most?
The one that intrigues me the most is the big picture, how you can understand this whole picture of what has happened to the universe over its entire lifetime. That's what I appreciate. I would call it the overview effect. I've always been in love with big picture and the comprehensive view of the entire universe, because that's, I think, one of the best ways to figure out who you are and how we got here. And that's really it's the big picture that I appreciate most about this. It extrapolates to earlier times than any other plot you will see. We've advertised it as the most comprehensive plot of the universe ever made. So I'll stick with that, and that's good enough for me.
A lot of it is very when I say conventional, I guess that's not the right term, but a lot of it is very agreed to physics in terms of how the universe evolved.
Yeah, it is, except for the first billionth of a second. And
funny that.
So, but the weird thing about it, we extrapolated all the way back to the Planck time. So we extrapolate like orders of magnitude in time, early and smaller in space as well. So it really does involve extrapolation to very, very early times and very, very small scales. But as you say, it's based on conventional understanding. And it could be wrong. It's very speculative. But when you're doing speculative things, I think it's very important that you be explicit. And that's what we are in this paper. We're explicit. And so that means if we've made a mistake, people can find it out and they know exactly what we did. We didn't wave our hands and say, oh, there's magic here. No, we said, hey, taking this normal conventional physics and extrapolating it in the most conventional way, this is the plot you end up.
Beyond here, there be dragons.
Well, beyond the Planck scale, there are dragons. That is, even in the plot, it has a region called sub-Planck Planckian unknown. So these are at times and scales that are less than the Planck scale, which is 10 to the minus 43 seconds and 10 to the minus 32 centimeters. So it's a very small scale in which people think that scientists have speculated, physicists speculated about space-time, and that's the name of your podcast, that there might not be space-time on a scale less than that. In other words, space-time might be discrete on the scale of the Planck scale.
So
and that's,
there was a time, I'm saying this positively now, there was a time when there was no gravity, but I can't imagine that time.
Well, you have to remember that as you get to higher and higher temperatures, these forces unite, and the gut scale is when the three forces, electromagnetism, the weak, and the strong, combine, and so you wouldn't talk about them as individual forces. Similarly, there's presumably a scale at which gravity joins them. That's the scale of the theory of everything, and so you wouldn't talk about just gravity back then because it will have been joined with the other three forces.
Does gravity have to be a force, but can it just be an effect?
Yes, I would agree with that. But when so it's an effect. And so I'm not quite sure how, if that's the case, and it might be the case, I don't think that gets around the idea that it's unified with these other forces. In other words, there's scales and energy. Well, one way to picture this very, very early universe is there. Imagine, how you have bubbles in a soda, pop, 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 coming into existence. Well, imagine that those are black holes coming into existence on the Planck scale. That would still be consistent with describing gravity as an effect rather than a force, but it would still also have to be combined with energies above the gut scale with strong nuclear force, weak nuclear force, and electromagnetism.
Is the universe simply a large-scale version of the Casimir effect?
Well,
things popping into and out of existence, basically?
Well, the relationship between normal matter and virtual particles, I mean, what you're talking about in the Casimir effect is that you're changing the structure of the vacuum. And the vacuum is, what is that? That's particles coming into and out of existence, and we call that virtual particles. The Casimir effect comes into existence only when you have two planes that are conducting very close together. I think you're right that you do have particles coming into and out of existence. You always have that type of noise. It's kind of like a virtual Brownian motion, and that is certainly true. On the other hand, the Casimir effect is when you take these two things and put them, two planes or two metal plates close, and then you change the vacuum but your question about whether the universe was a giant Casimir effect, that becomes an interesting question when you get earlier and earlier, because you have a space-time horizon. You have a c times a time. Let's say you get back to 10 to the minus 30 seconds after the Big Bang. And then you ask the question, well, wait a minute, does that constrain the virtual particles that can come in and out of existence? Is that like putting boundaries on the wavelengths of the virtual particles? I do not know the answer to that question. I've asked many theoretical physicists that question, and I am left confused, and I think they are confused about it. But it's a very interesting topic that I think will take more and more time from quantum cosmologists to figure that out. But it's a very good question.
The scale that you guys have come up with, it shows the picture. It doesn't really answer many questions, does it? It raises more questions.
Well, I think it does raise a lot of questions, and that's why it's called All Objects and Some Questions. But let's not underestimate the importance of showing all objects on one plot. The mere fact of doing that implies, well, for example, let me give you an example of what I mean. In Figure 1, we show the temperature history and the density history of the universe from the Planck time until today. Now, in order to do that, it's not that simple, because you need something called the relativistic degrees of freedom. In other words, as the universe gets hotter and hotter, there are more degrees of freedom over which to distribute the energy. It's kind of like when you have I'm not sure if you know high school physics where you learn about the degrees of freedom of a molecule. It can vibrate this way and that way and this way, and the more degrees of freedom it has, the more heat capacity it has, and that means you put energy in and the temperature doesn't go up. Why? Because the energy is being distributed over more degrees of freedom. The same thing is happening in the early universe. As you get hotter and hotter, the particles get more energetic, you have more relativistic particles around, and so you don't necessarily get a higher and higher temperature, because you can have your exciting different degrees of freedom. And that was a complicated thing that we had to understand, and we had to figure out what's the degrees of freedom as you go to higher and higher and higher and higher energy. It was very speculative, but we relied on the best data. for what's called G star, and then we just extrapolated that, and it could be this, it could be this, and so we had large error bars. But even though we included those large error bars, we propagated them through as good scientists should, and that led to the temperature result and the density result that we plotted. We also had to assume inflation at a certain time, and that's an interesting process to assume a specific model of inflation to talk about the temperature and density of the universe even before inflation.
Well, we haven't even explained cosmic inflation yet, have we?
It's a theory that seems to be...
It answers questions. It lets us know why the universe is so uniform in all directions, but it doesn't really explain why it happened and why it stopped.
You're right. On the other hand, one thing it does explain, and that is when you look at the cosmic microwave background at the largest angular scales, you see some anisotropies. And if you were just thinking causally and you didn't have an inflation period, you couldn't explain them. But with inflation, you can. And the explanation is, well, there are quantum uncertainties that you can't get around, and these have been blown up and expanded, and that's what we're seeing in the large angular scale cosmic microwave background. So that's something that cannot be explained in the standard Big Bang model, and so that's probably the best evidence for inflation, along with what's called n equals 1. That's the tilt of the spectrum when you plot it, of the microwave background fluctuations.
Do you include anything about dark matter or dark energy in your calculations?
Yeah. We assumed the lambda CDM, the standard model, and so we have an omega m. The matter is the dark matter plus the normal matter, and that's about 30% of the energy content of the universe, 70% is the lambda, and we assumed a Hubble constant of about 70. So we're just assuming the stock, standard, conventional lambda CDM model, and that's what we've plotted here. But that is important when you're talking about the temperature and the density of the universe as a function of time all the way back to the Planck scale.
That's Honorary Associate Professor Charlie Lineweaver from the Australian National University. And this is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. Scientists have discovered that the northern Greenland ice shelves are rapidly retreating and have already lost more than 30% of their total volume since 1978. The findings, reported in the journal Nature Communications, will mean severe consequences for sea level rise. Scientists used thousands of satellite images along with climate modelling to analyse glacier climate-ocean interactions in northern Greenland, finding a substantial and widespread increase in ice shelf mass loss. Since the early 2000s, they found that ice shelves that were once considered stable are mostly losing ice from the bottom due to warming oceans, and 3 of them have already collapsed completely. Of the 5 that remain, ice shelf mass loss is already destabilizing nearby glaciers, and they'll continue to retreat as the ocean continues to warm. For years, scientists have pondered the question of how starfish can survive with just arms and a body and no head. Well, it now turns out researchers got it all wrong. Starfish are pretty much all head. The problem is, starfish, or more correctly sea stars, don't fit the typical animal body pattern, with a head at one end, a torso and limbs in the middle, and a tail at the other end. To try and resolve the mystery, scientists at Stanford University and the University of California, Berkeley, undertook detailed genetic studies of the sea creatures. And they were surprised to find gene signatures usually associated with head development just about everywhere in juvenile starfish. On the other hand, the expression of genes that usually code for torso and tail segments were largely missing. The findings, reported in the journal Nature, also show that molecular signatures typically associated with the frontmost portion of the head were localized to the middle of each of the sea star's arms, with these signatures becoming progressively more posterior, moving out towards the arm's edges. The research all suggests that far from being headless, starfish pretty much lost their bodies to become nothing but heads, crawling along the seafloor. A full-scale investigation is now underway after mission managers were forced to initiate a self-destruct order on a Minuteman III intercontinental ballistic missile shortly after it was launched on a test flight from the Vandenberg Space Force Base in California. The self-destruct order was issued following an anomaly during the early stages of the test flight. Specialised launch analysis group has now been assembled to scrutinise the incident and determine the cause. With growing problems in the Middle East, Iranian surrogates attacking US and Israeli forces, Russia attacking the Ukraine, and China getting increasingly belligerent in the South China Sea, this wasn't the best time for a major missile failure by the United States. The failure also came as Russian President Vladimir Putin signed a new law revoking Russia's ratification of the Comprehensive Nuclear Test Ban Treaty. The 1996 treaty outlaws all nuclear explosions, including live tests of nuclear weapons. The Kremlin has repeatedly been threatening a nuclear escalation of its invasion of Ukraine. That comes in the wake of growing Western aid to Kyiv and ever-tightening sanctions against Moscow. Last week, Putin oversaw ballistic missile drills that were described as practice for massive retaliatory nuclear strikes against an unnamed enemy. These included the launch of intercontinental ballistic missiles from submerged Russian nuclear submarines. Unlike the American missile test, the Kremlin says the Russian tests were all successful. And now for something completely different. Just when you thought the Bermuda Triangle was no longer a thing, comes news of a new triangle mystery, this one in Alaska. Tim Mendham from Australian Skeptics says, forget Bermuda, the Alaska Triangle's the place to be for the latest in mysterious vanishing planes, energy vortexes, and strange UFO sightings.
Yeah, the Bermuda Triangle still exists at times. There's still a few examples. People raise it every so often when they need to explain. It's not really a big thing anymore. No, it's sort of passed out. But there's always a new one. And now there's the Alaska Triangle, which is an area of Alaska which is Utqiagvik, I think, and Anchorage and Juneau. And you make a triangle. Why it's always a triangle, I don't know. But they're saying that there are things like energy vortexes and mysterious disappearances. And there was a case that a leading congressman disappeared in the 1970s. I think he was in a small plane. And so they set up a big search party, didn't find anything. So you add magnetic irregularities, all sorts of different phenomena, hallucinations, auditory experiences, disorientation, etc. Naturally, this leads to the idea of a triangle with all sorts of mysterious forces.
Well, it's got to be. What else could it be?
Well, planes crash, people disappear down crevasses, hiding in caves and get an avalanche.
You get eaten by bears.
This is an area of wilderness.
You get eaten by bears?
Eaten by bears. This is an area of real wilderness where, a lot of things can happen to you and you get covered up pretty quickly, because especially if it's snowing, and your tracks can be covered up very, very quickly because it snows all the time in some areas. So like the Bermuda Triangle, there's no real mystery there. It's a created mystery. Now, they're using evidence, which is poor evidence, to substantiate theories of dangers, none of which exist.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to SpaceTimeWithStuartGarry.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGarry on Twitter, @SpaceTimeWithStuartGarry on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.